If you've been anywhere near software engineering lately, you know we're absolutely bombarded by buzzwords. NoSQL, big data, web scale, polyglot persistence. It's a lot, right? It can feel incredibly overwhelming to figure out what actually matters. But beneath all this rapid technological churn, there are enduring principles that hold true. So in this explainer, we're going to cut through the hype together. We're diving straight into Chapter 2 of our journey, looking at the fundamental architectural trade-offs in modern data systems, specifically this epic ongoing battle between the relational and document data models. By understanding the principles beneath the buzzwords, we can finally figure out how to choose the right tool for the job.
Okay, here's our roadmap for this explainer. First, we'll look at the relational database standard. Second, the object relational mismatch. Third, the document model solution. Fourth, the many-to-many problem. Fifth, we'll ask, are we repeating history? And finally, number 6, the great database convergence. Let's jump in. Part 1. The relational database standard, decades of dominance.
To understand where we're going, we really have to know where we started. And what's wild here is just how long this dominance has lasted. The roots of relational databases actually stretch all the way back to 1960s mainframe business processing. We're talking mundane tasks, customer invoicing, airline reservations. Back then, databases basically forced developers to think heavily about the internal representation of data on the disk. But in 1970, Edgar Codd proposed the relational model. It was this clean, theoretical idea to organize data into relations, or, what we now just call tables. Fast forward to the mid-1980s, and relational database management systems, and SQL, became the absolute standard. They successfully hid all those complex implementation details behind a clean, mathematical interface. And this unquestioned dominance, it lasted for about 25 to 30 years, which, let's be real, in computing history is an absolute eternity.
Moving on to Part 2, the object relational mismatch, the developer's pain point.
So, as application development evolved, a major complication reared its head. Most development today is done in object-oriented programming languages, right? But the data in a relational database is locked into tables, rows, and columns. Forcing your beautiful nested objects into flat tables, it just creates this massive disconnect. This right here is what we call the impedance mismatch. It's essentially an awkward translation layer that we are constantly fighting against. And sure, we have ORM tools to help reduce the boilerplate code, but they really can't completely hide the fundamental friction between these two entirely different models.
Think about a simplified data structure for a resume, like a LinkedIn profile. To store a single profile in a traditional relational database, your data literally has to be shredded. The main profile info goes into a users table. But then you hit one-to-many relationships. A user has multiple jobs, multiple degrees, multiple ways to be contacted. So you have to splinter all this data across separate positions, education, and contact_info tables, and then stitch them all back together with foreign keys. If you want to fetch just this one person's profile, you're stuck either firing off multiple separate queries or writing a messy, complex multi-way join. It's totally fragmented, and it absolutely does not match how a developer thinks about a profile object in their code.
Which brings us to Part 3, the document model solution, the JSON revolution.
This friction is exactly what paved the way for the NoSQL movement, as developers frantically looked for a better way. And for a data structure like a resume, which is essentially a self-contained document, a JSON representation is just incredibly appealing. Instead of shredding the data into 5 different tables, all those jobs, the education, the contact info, it's all nested directly within a single JSON tree structure. It's clean, it's intuitive, and it directly matches your mental model of the object. This explicit tree structure beautifully resolves the fragmentation we were just talking about.
And beyond just making the code a lot simpler to write, there is a very tangible performance advantage here. Because the document is stored together as a single contiguous unit, we get much better storage locality. If your application needs to render a user's entire profile, fetching it requires exactly one query. You don't have to bounce around performing multiple index lookups across half a dozen tables. Everything you need is right there, all in one place.
But here is Part 4, the many-to-many problem, when the tree breaks.
You know the golden rule of software architecture? There are no perfect solutions, only trade-offs. And data? Data rarely stays simple. As your applications evolve and grow, features get added. Suddenly, a company name isn't just a string of text anymore. It's a clickable link to a dedicated company entity, which has its own profile, its own employees. Boom, you've got many-to-many relationships. What used to be a simple, isolated tree structure is now a totally tangled graph. You've got multiple users linking to the exact same organizations, the same schools. That perfectly self-contained document model, well, it's not so self-contained anymore.
When you try to jam this highly interconnected data into a document model, you hit some pretty severe costs. In a relational database, you just write a simple join. Easy. But document models have historically had super weak support for joins, if any at all. So what do developers end up doing? They either have to emulate joins in their own application code by making multiple sequential database queries, or they go the denormalization route, literally duplicating the data across multiple documents. But if you do that, your application has to do all the heavy lifting to keep those duplicates perfectly consistent whenever something changes. Ironically, in trying to avoid the complexity of relational databases, you often end up writing significantly more complex application code.
All right, part 5. Are we repeating history? The 1970s rhyme.
This entire debate over how to handle many-to-many relationships, it actually isn't new at all. We really have to ask ourselves, are we just repeating history here? The whole SQL versus no SQL debate feels so cutting edge to us today, but technology is highly cyclical. Let's rewind the tape a bit and see how this exact same problem played out half a century ago.
So, back in the 1970s, the most popular database for business processing was IBM's Information Management System, or IMS. Fun fact, it was originally developed for stock-keeping in the Apollo space program. And here's the crazy part. Its design used something called the hierarchical model, which represented data as a tree of nested records. It is remarkably similar to the modern JSON model used by today's document databases. And guess what? Just like today, IMS worked beautifully for one-to-many relationships, but it struggled massively with many-to-many relationships because, you guessed it, it didn't support joins. The solutions proposed to fix that 1970s problem are literally what led to the invention of the relational model in the first place. Today's cutting-edge JSON structures are basically a rebirth of a 1960s paradigm.
Now, while the structures definitely rhyme with history, there are some modern philosophical differences, especially around schemas. Relational databases use schema on write. That's an explicit schema, where the database absolutely guarantees that all written data conforms before it's saved. Document databases are often pitched as schema-less, but a way more accurate term is schema on read. The structure is implicit. The data is only really interpreted by your application at the exact moment it's read. It's super similar to the debate between static and dynamic type checking in programming languages. And to be clear, neither is inherently wrong. Schema on read gives you amazing flexibility if your data formats are constantly evolving, while schema on write offers rock-solid guarantees if all your records need to share the exact same structure.
And finally, part 6, the great database convergence, polyglot persistence.
So how is the industry actually settling this decades-old debate today? Well, the reality is that the lines are blurring. You don't actually have to pick a side and declare a single winner anymore. Most major relational databases today have added native support for JSON, which lets you index and query deep inside nested documents. At the exact same time, document databases are actively bolting on support for joins so they can handle interconnected data much better. We've officially entered the era of polyglot persistence. This is where applications use a hybrid combination of different data stores, maybe picking a document model for self-contained profile data and a relational or even a graph model for highly connected social data. The models are converging because, honestly, they complement each other beautifully.
I want to wrap this explainer up with a pretty provocative thought from computer science pioneer Alan Kay. He argues that computing is basically pop culture, and the developers often have absolutely no idea where their culture came from. The NoSQL movement thought it was inventing something entirely new, when in reality, it was unknowingly wrestling with the ghost of the Apollo space program's database. Understanding these historical debates doesn't just make for fun trivia. It genuinely makes you a significantly better software engineer today. By looking back, we can finally see past the buzzwords. It really makes you wonder what other new paradigms in tech today are actually just ghosts of the 1970s waiting to be rediscovered.